Good day, grade 12 learners. Welcome to today's Physical Sciences lesson. My name is Tanwe Uwane. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. As you know that today's date is the 26th of January 2024, we are going to look at our physical sciences. The topic for today is going to be momentum and impulse. I know that you have already started with your teaching and learning. Therefore, most of you in your schools, you have already started with momentum. We will also like to welcome you in the year of 2024, as this is our first revision session in physical sciences. As I said that we are going to look at momentum. The momentum topic is under the knowledge area mechanics in physical sciences. It is plus or minus 10 marks, and it is normally question 4 of our paper 1 topic, question paper. Now, what is it that you need? These documents that I'm going to mention to you are the documents that you will always need to refer to every time you are looking at each and every topic that you are going to deal with in physical sciences. Remember, all the subjects that you are doing are policy bound, meaning that you need to follow some of the policy documents for you to be able to answer the examination at the end of the year. So what do we need? We will need your CAPS document. I know that most of your teachers will definitely make copies of the CAPS document, but you can also find the CAPS document on the website, because CAPS document is the document or the national document that we use for all our curriculum of any subject in South Africa. You also need your ATP. The ATP is the annual teaching plan. Some teachers are making copies for you to paste them on your class activity books or home activity books. So make sure that always when you are looking at each and every topic, you refer to that annual teaching plan. The exam guideline. Now, what is this exam guideline? The exam guideline is a guide that is provided by the examiners to say what is it that you expect at the end of the year. How will the question paper look like at the end of the year? Therefore, these are the documents that you must always refer to, because you need not to do things that are not expected for you to do at the end of the year. So go to the exam guideline and look at what is it that is expected, especially because today we are going to look at momentum and impulse. What is it that the examiner expects out of us as the grade 12 learner in order to answer our exam at the end of the year? This diagnostic report, some of the teachers, they will definitely use it, or you will also get it as the learner to see what some of the mistakes are normally done by you or by the previous learners in order for you to avoid them in 2024. Now, what are the objectives of this lesson? We are going to look at the definition of momentum. We are going to define the change in momentum. We are going to state the law of conservation of momentum and apply the principle in terms of the law of conservation of momentum. We are also going to define impulse and state and apply impulse momentum theory. We will also look at distinguishing between the elastic and inelastic collision and explain how the concept of impulse implies to safety considerations, and also define an isolated system and interpret the graphs on momentum. Now, as we all know, what is momentum? The first thing that we need to know in physical sciences, this is one of the subjects whereby, even though it's very closely related to mathematics, but there are also some of the things that you might not find in your mathematics, but you will definitely use the skills in mathematics to answer the questions in physical sciences. So what is expected of you is to start by defining momentum, because every concept that you are going to deal with, we must have an understanding of that concept. So how do we define momentum? So here we are given a definition of momentum to say is the quantity defined as the product. And as we are doing mathematics, we know that when we refer to the product, we refer to the answer that we get when we multiply. So it's the product of mass and the velocity of an object. That is why momentum is given a formula that says P is equals to mv, whereby we are going to multiply the mass of an object and its velocity. So remember, the m represents the mass and the V represent velocity. So that is the first thing that you need to understand about this topic. I will not emphasize less the issue of the importance of definitions. So always when you start each and every topic, just know the definitions. Note down the definitions. You can also make your own chart of definitions that you can plug in your bedroom, so that always you revise those definitions, because our definitions in physical sciences, they carry 2 marks, and 2 marks is enough for you to attain what you want by the end of the year. Remember, as we are starting with our physical sciences, we are all having 100%. So it means as you are continuing doing all the activities and the assessments and the teaching and the learning, you will decide whether you want to decrease your 100 or reduce your 100%, or you want to maintain your 100%, because we are all starting at 100%. We haven't written any exam, we haven't written any formal assessment by now. So all of us, we are still having 100%. So all what we are going to guide you on, it will always try to maintain the 100% that you are starting with on the subject. Now, we know that the equation illustrates momentum. It says momentum is directly proportional to the object mass and its velocity, meaning that as the mass of the object increases, or as the velocity of an object increases, the momentum of that object will increase. That is why we are saying the relationship is that the mass and the velocity of an object are directly proportional. So it means that when you increase the mass, you are also increasing the momentum of an object. When you decrease the mass, you are also decreasing the momentum, also with relation to velocity, because both the mass and the velocity, they are directly proportional to the momentum, which is the formula that we are provided. P is equals to mv. Now, from the definition of momentum, it is become obvious that an object has the large momentum if either its mass or its velocity is large. So if you look at the relationship, because the relationship is very important in terms of the proportionalities, you need to know what will happen if one of the quantities on the formula is increased. So this one is a very simple relationship of mass and velocity and the momentum. So we know that as we are increasing, like as we are having a greater acceleration, because you know the relationship between velocity and acceleration that we took down from grade 10. So as we are increasing the acceleration of an object, you are also impacting on the object's velocity. So it means, like, if there's an example like a bowling ball, if a bowling ball is rolling towards the pins of a bowling ball, if it is rolling towards the more the massive the ball, or the more the greater the acceleration it will have, the more the impact it will have on the pins. And remember, this is according to the Newton's second law. The Newton's second law, we did Newton's laws last year in grade 11, and we said also last year in grade 11, remember that the Newton's laws are progressing to grade 12, and they will also be integrating to more of the topics under mechanics that we'll be doing in grade 12. So as I'm saying, refer to Newton's second law. The first thing that must come into your mind, you need to state Newton's second law, because we are still going to state Newton's second law in terms of momentum. So you need to also remember what is it that we said last year in terms of Newton's second law. So we know also that as we are comparing, as we are decreasing maybe the acceleration, obviously we will also expect that there will be less of the pins that will be affected in a bowling ball, but that one is not as important. Now let's look at momentum in terms of solving of the problems. Remember, this is just a revision of what you have done with your teacher, and the main aim of this revision is to say, if there's something that you have missed during your lesson, then we are just emphasizing on what was done during the week. So this is not something new, because we are using the same annual teaching plan that your teachers are using. So let's look at this sample of a problem under momentum. A 2,250 kilogram pickup truck has a velocity of 25 meters per second to the east. Now, remember, the only thing that I forgot to mention as I started, you must understand that momentum is a vector. So momentum as a vector, it means always when you classify momentum, you must talk about its magnitude and direction. And we also know that velocity is a vector. So that is why the direction of this velocity or of this vector is provided. So they say here, what is the momentum of the truck? As simple as it comes. So what it means that now, according to Newton's second law, you know that when an object is accelerating to the direction of the force, it will also when a force is exerted to the object, it will accelerate to the direction of the force. And we said there is a relationship between Newton's second law and momentum. So when we calculate now the momentum of the object, what is going to happen? We are going to firstly write our formula, because for us writing a formula, we are confirming that this is the quantity that we are calculating, and we know the variables that are included in that quantity. So you are provided the mass of an object, which is a very simple activity that you can start with, because we need not to start very high as we are giving you these problems. We need to start at and try to scaffold them a little bit and a little bit, going to a higher order question. But this one is an easy and straight up question where you can be able to just substitute your quantities and find the correct answer. And such activities will also assist you to get familiar with your calculator. So what is going to happen here? You are going to substitute your mass, and you are going to substitute your velocity. Remember, our velocity, normally we write it as meters per second. Just that here we just write it as this one, because it's know that it's meter over a second, and second is also over 1. So for it to be meters per second, it means it's meter multiplied by second to the exponent 1 minus 1. I know that you know how to convert meters from exponent to decimals, so that one is not going to be a challenge. So here we have substituted our values, and our answer is 56,250 kilograms meters per second. And kilograms meters per second, already you know that those are the units to calculate momentum, because we have mass, which is kg, and we have velocity, which is meters per second. So for momentum, the units are going to be let me just write them here: kg meters per second. So that is why, and then the direction is also included as east, because we're told that the velocity of the object was towards east. So this is one of the problems that we can do at the beginning of the year, as you know that we are looking and we are using the formula P is equal to mv. We are not prohibited to calculate the mass or the velocity on the same formula. So you must know that sometimes the teacher can give you the momentum, and you need to manipulate the formula and calculate velocity or mass. So you need to know how to manipulate your formula. And in physical sciences, actually what we do, we always substitute on the original formula. If you are solving the mass problem, that variable that you want, it will always come out clearly after substituting on the same formula. So don't even try and make anything the subject of the formula to on the same formula that is original. Just use the values on that formula and find your needed variable. So as you know that we are looking at the entire momentum, we'll definitely try and just look at every scenario that we can expect under momentum, given this a little time that we are given, because this is definitely revision. Now let's talk about change in momentum. So what is a change in momentum? Change in momentum takes place when there is a force and time. So to stop an object, it is necessary to apply a force against its motion for a given period. So it is a measure of the difficulty experienced in the stopping of an object. So what is change? Remember, change is when you have delta P. So this delta P means change. What does change mean? It means on the change in momentum, we will have what? We'll have final momentum subtracting initial momentum. So when the final momentum subtract the initial momentum, we will definitely have the change in momentum. So already we have dealt with change in velocity, change in position, and those were the changes that we're looking at when we're dealing with other variables in our lower grades, especially in grade 10 and 11. So also the change in momentum, because this is a new topic that you're doing for the first time in grade 12, the change is still the same, where we say the final momentum subtract the initial momentum. In physical sciences, most of the concepts that we have done since grade 12, they don't change. And that is why when you look at most of the calculations, there will always be that integration between the previous grade and then I want us to, because we are now going to look at more scaffolded and more complex topics, I want us to take just a 1 minute break so that we just assimilate, or we just summarize whatever that we have already talked about during these few 15 minutes, where we look at the definition of momentum, where we look at how to use the formula of momentum, before we go further and look at how do we deal with the change in momentum. We'll just take a 1 minute break.
Believe in yourself. Believe a little more in yourself. Because to those that believe, nothing is impossible. You have done this before. You have passed your tests before. You have went into a higher grade before. It is possible because you have done it before. Do not doubt yourself. Keep believing in yourself. Keep pushing because this can be done and you can be great. Become better at what they do. Unsuccessful people do not plan, they just let life happen to them. But successful people are planning on how they want their lives to be. And right now, you plan on how you want your results at the end of the year to be like.
With the change in momentum. So we were saying that change in momentum, we know that when we talk about the change, we talk about momentum final subtract momentum initial. So that is what we mean by the change when we look at a final quantity subtract the initial quantity. So what is this change in momentum? Change in momentum is equals to impulse. So impulse is equals to the change in momentum. Therefore, you ask yourself, what is impulse? Remember the topic as it states on your exam guideline and also on your annual teaching plan and also on your textbook. It says it's momentum and impulse. Now, what is this impulse that we say is equals to the change in momentum? Now, impulse is a force applied on an object to the change of its momentum. So the product of the force and the time over which the force is applied. So when you look at impulse, you look at the product again. And product, we know, is this, the answer that we get in the product of the force and the time over which the force is applied. So that is why impulse is provided. The formula F net is multiplied by change in time. I think already you know the formula of impulse, and I provided the definition of impulse. So we are saying this impulse, which is the product of the net force and the time over at which the force is applied, is impulse, is equals to the change in momentum. Remember, momentum is equals to mv. Therefore, if we refer to the change in momentum, we said we are saying it's going to be the final momentum subtract the initial momentum. And we know that final momentum, remember, is going to be mvf, which we must also subtract mvi. So you can see that our mass is our common factor. Therefore, that is why here we can just say change in momentum is equal to m into final velocity minus or subtract initial velocity, because it is coming from here, because momentum alone is equals to mv. So this is what we refer to as our change in momentum, and this is our impulse, and we are saying impulse is equal to the change in momentum. Therefore, under the impulse momentum theory, the impulse experienced by the object is equals to the change in momentum. Remember, one of the bullets under our exam guideline, we're saying we must talk about the impulse momentum theory. So that theory states that the impulse experienced by the object is equals to the change in momentum, and we already concluded to say impulse is equals to the change in momentum. We know what is the formula of impulse. F net is multiplied by change in t, and we also know the formula of the change in momentum. So this is a very serious relationship that we must always remember. Now, this is what we were discussing on our previous slide in terms of what is impulse and what is change in momentum and how are they related. So we know that impulse momentum theory, as we said, impulse is equals to F net change in t. If we are looking for the F net, we can say change in p, which is change in momentum, divided by change in time. Therefore, is when we are looking for the F net or the net force. And then we know that change in p is the change in momentum. Remember, it's not momentum, but the change in momentum. And change in t is the time interval, is the time that, remember, we said over a certain time, the impulse of an object, the force experienced by an object over a certain period of time. Therefore, we need to look at the relationship between the force exerted on an object and the time that will be experienced on that force exerted. So we can see that the relationship between the net force and the time, or the time of contact, I normally say is the time of contact. So the relationship between the time of contact and the net force, the relationship is that they are inversely proportional. However, the relationship between the net force and the change in momentum, they are directly proportional. So it means, as you can see here, that we are saying F net is equals to M into Vf subtract Vi all over change in t. So you can see that now the relationship between the net force and the time of contact is inversely proportional, but the relationship between the net force and the change in momentum is directly proportional. In which scenarios do we use this principle of impulse? Because we need to know why are some of the things being discussed in our subject. Like, for example, if you look at impulse, most of the time it is used when we look at the safety features, especially safety features in time, in cars, safety features in some of the sports that you do. We know that now, if you know that the amount of force that you are going to exert is higher, it means the time of contact between you and the surface will be less, because what is happening is that impulse is inversely proportional to the time of contact. So if you are, for examples, for those people that are currently doing athletic sports, how will this assist you in order to know whether a person that is performing a specific sport will get injured or not? Let's talk about the high jump. We know that when you are doing high jump at school, you will always be given a sponge where when you, after falling from a certain height, you will fall on top of a sponge. So what is the purpose of you not falling on top of the ground? The ground, because it's a hard surface, it will allow a less time of contact. So it will be a less time of contact between you and the ground. And if there is a less time of contact, it means there will be more force exerted. Why more force exerted? Because we know that the relationship between the net force and the impulse is that they are inversely proportional. So for you to decrease the force that you will exert as you are falling on top of that object, you need to have more time of contact. So you will go through that sponge, and as you are going through that sponge, as you are falling to that surface, it will increase the time of contact, and there will be less force exerted on you. And as there will be less force exerted on you, it means there will be less injuries. So that is why I'm saying there are always reasons why some of the principles are learned in physical sciences. Also, when you look at the car features, you know that our cars are also having those safety features that will assist you in order to reduce. We are not saying they will stop, but they will reduce the injuries. So we have things like airbags in our cars. We know that how dangerous it can be when you hit the windscreen and as compared to when you hit the airbag. And when you hit the windscreen is having a hard surface, and as it's having a hard surface, it will also make a less time of contact. And if there's less time of contact, it means there will be more force, because we know that the net force and the time, let me just do this, and the time of contact, as the other one increases, the other one decreases. So when you have less time of contact with that surface, there will be more force exerted on you. So when you are especially when you hit a windscreen as compared to hitting an airbag, it is the reason why you get injured more on a windscreen as compared to on the airbag is because there will be less time of contact with the windscreen, and there will be more force exerted on you. And remember, if there is more force, you will exert more force on the windscreen. And according to Newton's third law that we did last year, if you exert a certain amount of force on a surface, the same surface is exerting that same force to you, but in opposite direction. So if you will be exerting 40 newtons or 80 newtons to the windscreen will also exert the same amount of force. But when you are hitting a soft surface like an airbag, so the airbag will allow you to go through in it, so that there will be more time of contact between you and the airbag. And as there will be more time of contact, and it means there will be less force exerted on you. So that is why must always be a reason why we are doing some of the principles in physical sciences. So let's look at the relationship, because the force needed for the change in momentum. Now here is a problem here, which is also another example. A 1400 kg car moving westward with a velocity of 15 meters per second collides a utility pole and is brought to rest in 0.3 seconds. Now, when we are dealing with calculations in physical sciences, the first thing that we need to identify, we firstly need to identify the variables. You need to have your data. You need to have a data, the information that is provided on the question, so that you immediately know what variables do you have, and if they are looking for a certain variables, you need to know which correct formula can you use. And all these formulas I know already, because this is our strategy. They are provided to you. You are provided the formulas of momentum. You are also provided the exam guideline. And what was supposed to happen is that you are supposed to paste those formulas on your classwork activity. You are also supposed to paste the exam guideline. Why the exam guideline is important? As I said, you will be ticking all the bullets as you are going through each and every bullet with your teacher, meaning that you and your teacher, you are assisting each other in order for, at the end of the day, when you are done with the topic, you'll just say, just this is that, because I know the meaning of every bullet and I know what is understood by every bullet. So here is our data here. This is what we want you to do always when you are dealing with each and every topic, solving a topic, especially when you are dealing with what? With calculation. So they say here, find the magnitude of the force exerted on the car during the collision. So that is what definitely the question is all about. So we are provided the mass, we are provided the velocity of an object, we are provided the initial velocity, because remember, it started at 15 meters per second and it was brought to rest. So immediately when you see words like rest, already there is a hidden data that is provided to you. The examiner is telling you that it started by moving at 15 meters per second, but at the end of the day it stopped. So it means we have the final velocity and the initial velocity. So when you see word rest, already we know that rest indicates that is 0 meters per second. So it starts at 15 and goes to 0 meters per second, which is your final velocity. So that is why here we are saying our initial velocity is 15 meters per second and our final velocity is 0. So don't be surprised, where is 0 coming from? You are told that it will stop, and when something has stopped, it means it is not moving. And if something is not moving, it means its velocity is 0 meters per second. And when you are provided with the time of contact between the car and the utility pole, now we are looking for our variable, which is force. So already with this information, you can go back and say F net, let me just put net here, is equals to our change in momentum over our change in time. So which is going to be M is equals to M into VF minus VI over change in time. And then we are going to substitute our values on the formula. Remember, the velocity, the mass of the car will not change when it is when before it hit the pole and after it has hit the pole. So the mass is the same. So that is why the mass is we just take it out as our common factor. And then our final velocity is 0. And our initial velocity is 15 meters per second. Therefore, you can see that now. Remember, we were told that the car was moving westwards. So it means our west, if you choose our west as positive, anything that will be against anything, if our answer or our final answer becomes not, it doesn't become positive, it means it will be the opposite direction of it. So if you choose west as positive or negative, let's say we choose west as negative. If west is negative, it means here it was going to be positive 15, but because our west is positive, it means now, so we said 0 subtract. Remember, subtract is not for the direction, subtract is for the formula. So we have taken our 15 meters per second, which is our westward, as positive. Therefore, our answer becomes negative 70,000 kilograms per meter squared. So you can see that now this was westward. It was moving westward. So it means, I think the direction was supposed to change, because remember, if we are taking west, again 15 is for our west as being positive, it means our direction was not supposed to be. If it is now giving us the negative number, it means it's going opposite to our direction. So I don't think that it was supposed to be, but I think it was supposed to be it's because we are opposing the motion of an object. I think this one you can also look at it as you are going to look at this problem. But definitely, if the opposite direction, if here it was minus 15, then it means we have taken westward as negative. Therefore, our answer was going to be positive, and we're still going to say it's towards east. So direction is very important as you are doing your calculations, and you must know that you are dealing with vector quantities. So always you must be mindful. What do we say? Sign conversions, as we did them last year, they are still very proper for you to do this momentum. So it is very important to go back to it. Also, this one is another question on momentum. It's also a worked example where we look at how do we calculate the net force. And when we calculate the net force, here I like it because they gave you see, they even said, if you are putting negative, you are saying west. But if you just put, because our answer actually in physics, it must not. So that is why here, because my answer, I was supposed to say 70,000, and then I was supposed to be east, because actually we are not encouraged to leave our answer as negative. We need to leave them as positive. So that is why when there is negative here, this west is definitely not going to assist that, but we can say 70,000 kilograms per meters per second east, so that we don't leave our answer big negative. So that is why I was saying this negative and this west, actually we need not to leave our answer like this, because we know that it's an opposite direction. So it's 70,000 momentum to the opposite direction, which is east. Let's leave this one because it's almost the same as that one. This one are just scenarios that we can expect on the momentum, and also on the reason why they were included is just for you to even understand more the application of the law of momentum. So you know that when you are when a certain force is exerted on you, there will always be the relationship between the time of contact between you and the surface and the force exerted on you. So these are just few examples that we gave so that you understand the relationship between the net force and the time of contact, or the net force and the time that is experienced over the force that is applied. Okay, let me just go back. So remember, we said we will also look at the safety features. So this is one of the examples that we can look at. As I was saying, when you look at this is just a story on how the airbags work and what makes the airbags to pop out during injuries. And you must understand that all the laws that we learned last year, the Newton's laws, starting from the Newton's first law of you, is it important for you to always put on the safety belt? Remember, that is not a seat belt, that is a safety belt, because the main issue of that belt is to protect you. So putting the safety belt will also prevent you from getting or hitting the windscreen, which will definitely apply a certain force on you. And some of the cars, when the airbag, when the seat belt, when the safety belt is not on, they normally don't even release the airbag. So those safety features, we are learning them in physical sciences so that they can inform some of the decisions that we take when we are inside cars or when we are traveling. So here is an example of an airbag, a person being hit by an airbag. So we said, remember, if there's a difference between being hit by a windscreen and also by an airbag, because an airbag will do what? Will reduce the time of contact. So it means they will be will increase the time of contact and reduce the net force. So what will be reduced when you hit the airbag? It will be the net force, but there will be more time of contact between you and the airbag. So all the story that you see here, they are just emphasizing why is an airbag important and what exactly is happening when you hit an airbag during a crash. Also, our cars, they have something that we call a crumple zone. So the reason for the crumple zone, they design it also so that when you undergo, because you need to know what will save you during the impact, during the time of impact, or during the collision. So the crumple zone is also used as a feature in most of these modern cars, so that as you got the impact, the car, they say it crumbles like in this picture, so that at least you don't get more injury, so that they will be the crash, most of the objects on the car don't hit you, and as they hit you, they will exert a certain amount of force on you. So the car will crumple by absorbing part of the impact from the crash, and the crumples will have been credited as the save, or it has saved thousands of lives. We are not saying, guys, when these features are there in our cars, there is no way that you can get injured, but at least they reduce the impact, they reduce the form of injuries that you can get, because they are used, and all of them, as you see them, they will always try to increase the time of contact between you and some of those surfaces that you will be in contact with in the car, so that there will be less force exerted on you and there will be more time of contact between you and those objects. So those are the things that, so they are saying this is how the crumple zone works, and definitely this was one of the initiatives that was discovered by the engineers. But the engineers, remember, they used physics principles to come up with all those safety features. So the relationship between impulse and momentum, that is why it is important for us to understand why. And so for those that are going to be engineers in the future, definitely you will be, at the end of the day, be expected to use such principles so that you can come up with safety features. Also, as I was saying, that in terms of the sport that we are playing, I cannot emphasize enough the importance of the use of the principle of impulse. When we are having different sporting codes, like we have soccer, we have what we call golf, we know that even the balls that we use for those posting codes are not the same. Even the material that we use for those posting codes are not the same. And all the reason why they chose different materials for those is the principle of impulse, because we will say, we know that we are always in contact with the ball of soccer, volleyball, because you are using your palm. Obviously, it must not be as hard as soccer ball, but it must be as softer, and the soccer ball is not also as hard as a golf ball, because in a golf you are using a golf stick, you are not in contact with that ball. So all those principles, they use impulse. Now let's look at conservation of linear momentum. We have spoke about momentum, we have spoke about the relationship between impulse and the change in momentum, and we have also talked about how do you use the principle of momentum and impulse. Now we look at the conservation of linear momentum. I think we know by now linear means straight line. So we are going to look at the conservation of momentum in a straight line. So the law of conservation of linear momentum states that the total, you see this word is very important, the total momentum of an object, of all objects interacting with one another remains constant regardless of the nature of the force between the object. So we are saying under the conservation momentum, in an isolated system, momentum will be conserved and the total linear momentum of all objects will remain the same, meaning will remain constant. So this is the law of conservation of linear momentum. This law is also stated to you on your exam guideline. So if you look at now, remember when we talk about momentum and the linear momentum, we talk about now the collision. So it means when, like in a case where we're referring to a car hitting the pole, we know that the momentum of the car before hitting the pole must be equal to the momentum of the car after the impact, after hitting the pole, after the collision between itself and the pole in an isolated system. Remember, in physics and in physical sciences, we normally make our systems to be isolated so that we limit the variables that we deal with. Because if we don't limit the variables, there will be lots of reasons why, how about this, how about that. So dealing with an isolated system, especially when we are dealing with our calculations, will always assist us to limit the variables. So let's look at this example. We are looking now at the conservation of linear momentum. Soccer ball collision. Before the collision, we have ball A and ball and B. Before a collision, ball A has momentum PA and ball B has no momentum. It means ball B was stationary or was at rest. And then after collision, after collision B, ball gains momentum PB. So let's say we have ball A of mass 0.4 kg and the velocity of ball A is 0.8 meters per second. Ball B obviously will have mass, even though we say its momentum is 0 or does not have momentum, but the mass of the ball will be there. What will make the momentum of ball B to be 0 is because it is at rest, it is not moving, it is stationary. So those are the ways that we normally see during our examination, stationary or at rest. So you can see that you can be able to calculate the momentum of ball A. How did we calculate the momentum of ball A? We know that P is equals to mv. So this is the momentum of ball A. We'll say 0.47 multiplied by 0.84. And then we'll get the momentum of ball A. However, the momentum of ball B will be 0 because we know it's going to be 0.47 multiplied by 0, which will give us what? 0 meters per second. But now, according to the law of conservation of momentum, it says the total linear momentum of an object remain constant or is conserved. Meaning that how do we now calculate how do we use the law of conservation of linear momentum? I will not even say conservation of momentum. I will always emphasize the issue of linear because we are dealing with motion of what? Of straight line. So we know that it means now the momentum before collision. So it means momentum before collision. It needs to be equal to momentum after, let me say momentum after collision. So momentum before collision must be equal to momentum after collision. Remember, this is momentum before collision and this will be momentum after collision. So already, if we know the momentum of this object before collision, it will be equal to the momentum of the ball after collision. So we are going to use the law of linear momentum to find that. So this is how we are going to solve this problem. So total linear momentum is equals to 0,04, and then after collision it will still be the same 0,04 kg. So how did you find that? Remember, it's going to be the initial momentum before collision is going to be the momentum of what? Of pole A, and then which is going to be, and then the momentum of pole B was 0. After collision, it's going to be, remember, we are going to calculate using that formula, momentum before is equals to momentum after, which is going to be, we can say M1 V1 plus M2, remember, is the sum, ne? Total is the sum. So that's why I use plus, total linear momentum. M1 V1 is equals to plus M2 V2, or I can say MA, because it's pole A and pole B. Remember, we can label the way we want it because we are provided with the symbol. A mass of pole A multiplied by velocity of pole A plus mass of pole B multiplied by velocity of pole B is equals to mass of the final mass. Again, here we can say VI, and then here we can say the mass of pole A, VF, plus the mass of pole B, VF. So the final velocities, and the, so from here you are going to substitute the mass of pole A and the initial velocity of pole A you are provided. It is 0,04, and then you are going to put the mass of pole B, which was 0,747, and multiplied by 0, which is, so that is why at the end of the day, what you think it will be there is only the mass and the velocity of pole A that will look like it exists, and we expect it to be equals to the final of pole A and final of pole B. That is how we calculate the conservation of linear momentum. So you equate the momentum before collision and the momentum after collision. As you are doing that, you are proving the law of conservation of linear momentum. So that is why here you can see that they've tried to solve the two problems to find what is the, how do we relate the two momentum. So as you can see here, we have two cars colliding and they are coming in opposite direction. Remember, the sign convention is very important, especially when you substitute the velocity. So we expect that before collision, these two will have different momentum. There will be momentum of car 1 and there will be momentum of car 2 before collision. And we expect that the momentum of the two added together before collision must give us the same momentum after collision, because according to the linear momentum, the two is conserved. But normally we don't calculate the momentum before and after collision. Maybe we can calculate the final velocity after collision or the initial velocity. It depends on how the examiner will ask us to manipulate. So you can see that here, after collision, this is what is going to happen. And definitely here, when you look at this principle, Newton's third law, because remember, the two objects will collide, and we must never forget that if the two objects exert a force on each other, definitely Newton's third law will come into place to say, if we know the force that one object exerts on the other, there's no need for us to calculate the force that the other object exerts on the object that is, because already we know that they exert the same force but in opposite direction. So that is why we say that here, normally when there's a force exerted, when one object is exerting a force on another object, definitely Newton's third law will come into place. And we have seen also that under momentum, there was also a relationship between Newton's second law and momentum. So all the Newton's laws that you did, definitely you need to revise them, because they will also be used here. If we know that car A is exerting 80 newtons to car 2, or to the second car, obviously we will know that car 2 is exerting minus 80 newtons, because we will know that we will be referring. So sometimes an examiner will say, this is the force that is exerted by this object to this object, what is the force that is exerted, and sometimes they will sometimes not expect you to calculate by no use of a calculation. So by no use of a calculation, it means definitely we must conclude by using a principle in such scenarios. Okay, so here, as I was saying, that the relationship between Newton's third law and momentum, to say for every reaction between two isolated objects, the change in momentum of the first object is equals to and opposite to the change in momentum of the second object. And that is why I was saying this was definitely taken from Newton, because remember, the change in momentum also talks about what? Talks about the change in velocity, because we know that if we talk about the change in momentum, we talk about the final velocity subtracting the initial velocity. So this is the relationship between the momentum as we look at the Newton's third law. So I think this is the one that I was talking about, of us calculating the conservation of linear momentum. I think because we'll be dealing with different objects of different velocities, of different masses, it is very important for you to write and label the symbols correctly, so that even when somebody is marking your problem, the person knows what are you referring to as MA or MP, VA or VP, M1, V1, M2, V2. At least you give direction to the person that is marking your script to say, what is it that I'm talking about? This is the mass of the first object. This is the velocity of the first object plus the mass of the second object, the mass of a. So that is why here we refer to our velocities as I and as F, because we know that during that collision, definitely there will be some change in momentum. And in change in momentum, definitely is normally and always determined by the velocities, because the velocities are the ones that are going to change and not the mass in terms of the conservation of momentum. We are going to take definitely a 1 minute break, and after that we are going to look at how do we deal with more complex questions in terms of the conservation of momentum and different types of collision. Welcome back, grade 12s, as we are busy dealing with the conservation of linear momentum and looking at how do we calculate the conservation of linear momentum. What I was emphasizing before break, I was emphasizing the issue of we need to definitely be able to label our calculations, or we label our variables, so that we know what is it we are dealing with, because these values, there are many, especially when you are provided equation. So you need to know what is it that you are dealing with, especially when, like in this equation that is here. I'm giving all these examples so that when you are dealing with any other activity, you always go back and refer to these worked examples, so that you can see how were the solutions made out of this. A boat of 76 kilogram, a boat of 76 kilogram, initially at rest, not forgetting, normally when I'm provided such weights, I will encourage you to write at the top 0 meters per second, so that you already know that there is a value that I have for that specific object, which was not written in as number, but was written as a weight. So write it at the top to say 0 meters per second. At rest in a stationary 45 kilogram boat. it steps out of the boat onto the dock. If the boater moves with a velocity of 2.5 meters per second to the right, what is the final velocity of the boat? So we are looking for the final velocity. So the 2.5 meters per second is for the boater. The boat is the one that is at rest. So we want to know what will be the final velocity of the boat after the boater has stepped out of the dock onto the dock. So you see, when you look at all these values, if you can't organize your data, you might start by having a problem of even which formula do I use, where must I substitute. So writing all your data, there is a boat, there is a boater. You need to know the mass of the boat. You need to know the mass of the boater. You need to know the initial velocity of the boat, the initial velocity of the boater, the final velocity, all of them, all that information. You need to know it before you start using any formula. So here, the mass of the boater, we were told that is 76 kilogram. The mass of the boat, we were told that is 45 kilogram. Then the boater was at rest, and the boat was also at rest. Remember, we were told that both the boater and the boat were at rest. They were not moving before the boater decided to move out or to step out. Now, after stepping out, we find that the final velocity of the boater is 2.5 meters per second. So what we are looking for is the final velocity of the boat. So if you have stated all your data like this, then the next thing you know is that you must go straight to the formula of conservation of linear momentum, where you are now going to substitute your values and find the final velocity. And according to the conservation of linear momentum in a closed system, we are saying the momentum before collision is equals to the momentum after collision, whereby now we are going to look at the initial momentum, which is going to be our, remember, we say m1 v1 plus m2 v2, and both the boater and the boat were stationary. So that is why our initial momentum is 0, but it cannot be like you just write 0. Substitute the values. Let them 76 gram multiplied by 0. Let the 45 kilograms multiplied by 0. So that at the end of the day, you know that your initial momentum is what? Is 0, or the momentum before collision is 0. And then after that, we are going to find the, remember, we are looking for the, so you can even say, if you know that this one is m boater v1 boater, just for you to, it doesn't mean that you just have to say 1, 2 or ap. You can label your diagram in any way. So here we are now looking for what? We are now looking for the final velocity. So here they're just showing you how they got there. But we know that the final velocity must also be 0. So after we find the final velocity of the boat, when you add the right hand side, it must also give you 0. But now they didn't want you to calculate the final momentum, because you are just gonna say 0 kilogram meters per second. They just want you to calculate the velocity of the boat after the boater has stepped out. So when you, after getting that velocity, you need to go back and prove that the final velocity, the final momentum is also 0, as we know that the initial momentum is 0. So, but here you will be looking at m1 vf1 plus m2 vf2. Then the mass is 76 multiplied by, remember the final we're given as what? As 2.5 plus the mass here was how much? Was 45 multiplied by vf2. So what you are going to solve here, you are going to find vf2, and then after getting vf2, you are going to take that value of vf2 and substitute it here and add everything, and everything after adding it must give you 0, because you said you are saying momentum will be conserved, meaning that the initial momentum will be equals to the final momentum. So you will take that value and substitute it here, and then it must give you 0 kilograms meters per second. Even if the answer is 0, we know that in physical sciences we need to always indicate the units. So our units, we are not saying is 0 multiplied by the units, therefore the answer is 0. Our units, we are saying our momentum is 0. And we know that momentum, each unit is kilogram meters per second. So dealing with conservation of linear momentum, the most important thing that you need to know that momentum in an isolated system is conserved, and all the definitions are provided to you on the exam guideline, and all these formulas are also there on your data sheet that your teacher gave you. We gave you the data sheet of momentum only so that you know the formulas that are needed for momentum, so that you know how to use also those formulas under momentum. And then now we said definitely there will be collision. There will be a collision between objects during momentum, and it depends whether the collision, at the end of the day, there will be energy lost, or sometimes in that collision there won't be any energy lost. That it means now we can even go further and say if two objects collide with each other, will be any loss of energy, or an energy will be conserved. And that is why we look at types of collision. But before I go to types of collision, I think under the conservation of linear momentum, we need to know different scenarios that an examiner can expect or that can be examinable. We know that number one, I normally say, if you are done with the conservation of linear momentum, you must deal with all the scenarios that are included on the conservation of momentum. Sometimes you'll find the object colliding and separate. So you'll find that two objects collide, and after collision, they separate. Or sometimes you'll find that two objects collide and move together. Sometimes they move together, and some of the textbooks, they will definitely confuse you. They will add the masses of the two objects, and you'll wonder why are the object now masses added. Remember, as they are moving together, it means they will both move with the same velocity, so their masses will be added and they will have one velocity. So you need to have where objects separate, where objects move together, and also you need to deal with explosion, whereby an object was together and it separated after collision, like a rocket. When a rocket moves, explode. So those scenarios, I think and hope that, because they are also stated on our exam guideline. Remember, we won't be able in this session to look at each and every scenario, but those scenarios, we need to make sure that we look at them, because when it is explosion, it means the mass was one and there was the same velocity before collision. After collision, as they separate, definitely there will be two objects with two different velocities. So those are the scenarios that we look at, especially when we deal with the conservation of linear momentum. So go back and look at whether all the scenarios we covered as we are looking at conservation of linear momentum. So I was also saying here, we will look at types of collision. We have two types of collision. The first one is inelastic collision, and the other one is the opposite of this one. And we normally say it's a perfectly inelastic or perfectly elastic collision. So when two objects collide and move together as one mass, they stick together after the collision, like the meteorite and on Earth. They say the total kinetic energy after collision is less than before. So that is when now you will see that some of the energy was lost in the system and the collision doesn't become elastic. So what is inelastic collision? Inelastic collision is experienced when energy is not conserved. And the examiner will say to you, is the collision elastic or inelastic? How do you prove that? You just need to prove whether energy is conserved or energy is not conserved. Where energy is conserved, it means collision was elastic. When energy is not conserved, it means collision was inelastic. Yes, as I was saying, it's inelastic. So what you do there, remember, we are going to deal with energy principle. And because, remember, there is a movement of objects as they collide with each other or as they separate with each other, there will be movement. So the only energy that we're going to refer to it in this particular instant is going to be our kinetic energy, the energy of motion. So we are saying in the conservation of motion, if now when you look at the conservation of momentum, at the end of the day, you find the two objects, this is masses staying together. Definitely the collision here will be inelastic because it means there will be energy loss in the system. Like when you have two cars, car M1 and car M2, when they collide and stick together, you remember I said we normally add their masses because they will move together with the same velocity. The total momentum of the cars before the collision is the same as the two cars after collision, but the collision in this form, it will be inelastic because we are saying here energy will not be conserved. If you look at this example here is a 1,825 kilogram luxury sardine stop at the traffic light and is struck from the rear is the back, because rear by a compact car with a mass of 875 kilograms. The two cars becomes entangled, they come together. If the compact of the car is moving at the velocity of 22 meters per second to the north before collision, what is the velocity of the, so here we want the velocity of the car after they combined, after they entangled with each other. So obviously it means you will have two cars. This one has stopped at the traffic robot, and this one is the one that hit the, and the car which hit this one was at the velocity, was moving at the velocity of 22. So we want to find the velocity of the cars after they move together. So obviously it's gonna be what? It's gonna be the M1 V1 plus M2 V2. We expect, remember, we expect the momentum before to be equals to the momentum after. Let me say VI and VI. And then here it's going to be M1 plus M2. Why M1 plus M2? Is because they are now moving at the same velocity. So you will substitute, this one is going to be 0 because it was at rest. This one, it was its mass and the velocity of 22 meters per second. After that, so it's going to be 0 plus that one of 875 multiplied by 22, then which is going to be equals to 1825 plus 875 and then VF. So you will find the velocity, the final velocity of the two cars as they are moving together after the collision. So this, obviously this one is one of the examples that we told that here it means the collision was inelastic. So this is what is going to happen. As I was saying, we're going to find it. This one is the initial velocity before collision. The 975, don't be confused, it is coming from the two masses added together because it's going to be mass 1 and mass 2. There's no need for you to do this step as I said, because we don't encourage it definitely to make anything the subject of the formula. You can just go straight here as I did on the previous slide and put all the values on the same formula. But remember, the masses here are now added together because the two objects will be moving together and find what? The final velocity. And because as I was doing my calculation, I made all the direction positive of our 22 meters per second. So definitely our answer will also be 7.59 meters per second, and the direction is to the north. Remember, this is the final velocity of the two cars being embedded together. So don't be surprised when the two masses are added together. It's when the cars move together after collision. And then then the second collision is elastic collision. So two objects collide and return to their original shape with no change in kinetic energy. Here again, we are going to still use, we are still dealing with conservation of momentum, but we are just asking whether there will be energy loss or energy not loss. So we are saying most collisions are not, they are not inelastic or elastic due to energy losses and deformations. So definitely we are going to look at whether energy was conserved or energy was not conserved. And when we deal with elastic, we expect that energy before collision must be equal to the energy after collision, meaning that energy must be conserved. So we are also having a way of proving, like this one is just an example to say the two balls collide and they separate, and definitely the two balls will not change shape, they will not be deformed, they will go back to their original condition as they were before collision. So obviously this kind of collision will be what will be elastic. As I'm saying, both balls have the same mass, both balls move towards each other, be with a higher velocity and thus higher momentum, and after collision, as they separate, the collision will be elastic, because as I'm saying that after separation there won't be any form of loss of deformation or whatever. So let's look at, okay, now when we talk about energy, conserved energy, we are not referring to momentum. Momentum will be conserved. Remember, momentum in an isolated system will be conserved. So what will happen in an inelastic collision? We expect momentum to be conserved, but what will not be conserved is energy. Momentum will be conserved, and these are some of the multiple choice questions to say during elastic collision what will happen. Energy and then they give you momentum, and then they give you energy, kinetic energy, and definitely they will sometimes be specific, say kinetic energy, or they'll say energy, and then they say momentum conserved, energy conserved, momentum conserved, energy not conserved. You understand such. So you need to know that even in an inelastic collision, momentum will be conserved, but what will not be conserved is energy. So but your duty is to prove that the collision is elastic or inelastic using those collisions. So we are still saying the momentum will be conserved in this type of collision. I want us to go to a point whereby we will be looking at those collisions. So we are still saying the momentum will be conserved in this type of collision. I want us to go to a point where now we are proving that momentum is conserved or not conserved. Like when we are given the scenario like this one, we need to calculate the kinetic energy before collision, before collision, like before collision, and the kinetic energy after collision. You see, when you want to check, and how do you calculate EK? You know that kinetic energy EK is equal to R M D squared. And how do you calculate? So you will check whether kinetic energy before collision is the same as kinetic energy after collision. Like when you say the two objects collide with each other, like the two objects that are provided here, so you will find their kinetic energy before collision and you will equate it with their kinetic energy after collision. So you will have the masses of the object and the velocities of the object, so that you can be able to use the formula half mv squared to find the EK in joules before collision, and then you compare it with the EK after collision. If the values, let's say we have the 2 joules before collision and the 2 joules after collision, if the two values are the same, and you don't equate, you don't say EK before is equal to EK after. We don't conclude before we calculate. To say it's elastic or inelastic, you must find the kinetic energy before collision and the kinetic energy after collision. Then you come up with the conclusion to say the collision is elastic and inelastic. And to say collision is elastic or inelastic, you need to definitely say it as a statement and state it, because the question will say, will this collision be elastic or inelastic? So that is why I'm saying we don't say this EK before is equal to EK after. This is incorrect. Calculate EK before collision and calculate EK after collision. Compare the two claims between before collision and after collision. And then you come up with a conclusion to say, is the collision elastic or inelastic? We know that we are also expected to read and after questions under momentum, because remember there will be collision, and we can also deal with questions under pendulum. I think you all already know what is a pendulum. This kind of motions, the motions that are moving in this direction, you see this kind of motions, the motions that are swinging, the swinging motions. So as we are dealing with momentum, you can also be expected to deal with questions that deals with pendulum. So like in cases like this one, this is an example of a momentum. Like when you can see here, there is a 5 kg block and there is a bullet that is swinging. So definitely, and you know what I like about this is this, because this definitely it makes you to remember the principle of conservation of what? Of energy. Remember the principle of conservation of energy that we did in grade 10. It is still very handy in grade 12, especially when you are gonna deal with what? With principle where with calculations where we are including what? Pendulum. What did we say about principle of conservation of energy? We are saying energy in an isolated system, energy is being conserved, meaning that energy, we normally say EK, changing EK at the, I normally say EK at the bottom, or mechanical energy, because that is why mechanical energy is a principle of conservation of mechanical, mechanical, not chemical. Mechanical energy. Mechanical energy in an isolated system remains constant, meaning that throughout the motion of an object, if the system is isolated, we expect the energy to remain the same. We expect the energy to be conserved. So even if this object is here, the energy is the same. Even when the object is here, the energy is the same. Even if the object is somewhere in between, the mechanical energy of the object is the same. So we normally say at the top, the mechanical energy is equal to the gravitational potential energy. So at the top, EM, which is mechanical energy, is equal to what? Is equal to mgh. And then at the bottom, we normally say EM is equal to half mv squared. And we know that why at the top, or somewhere halfway, both of them, we have both EK and EM. But when we are at the rest, we have only gravitational potential energy. When you reach the surface of the ground, like when the object is dropped, at the top before it's dropped, it's having gravitational potential energy. When it reaches the ground, what is the maximum is going to be its kinetic energy, because at the ground, its height is going to be 0, but at a certain height, its height is at its maximum. Here, the velocity is at its maximum. So that is why we normally refer to the kinetic energy at the top being gravitational potential energy that is taking preference, and kinetic at the energy at the bottom being kinetic energy. But we know that the principle says EM is equal to EK plus EP. Normally say change in EK is equal to change in EP. This is the principle, because we are saying mechanical energy is conserved throughout the system. So when you are dealing with pendulum, that is why when you look at this, they can also ask you, calculate the gravitational potential energy. This is a bullet before it hit this block. So they can even say, calculate the bullet and the block gravitational potential energy here at this system, because this was a bullet and this was a stationary block. The bullet hit the block, obviously there will be collision between the bullet and the block. So there is a relationship of momentum and energy already in this kind of an activity. And then after that, after hitting the block, the board or the box bullet system started to swing like this to this height, and the height was 15 centimeters. Already we know that when you are given units which are not SI units, you know that it is very safe for you to firstly start by doing what? By converting the units. And if you are given centimeters to meters, we know that you must divide by what? By 100. I know you are mostly used to millimeters that you are dividing with 1,000, but definitely you must know how to deal with picometers, centimeters, millimeters, so that you know how do you convert to meters, because we know that meters are our SI units for distance or height. Then if they can ask you about the gravitational potential energy of this bullet at this point, then you know that at this point we are going to use what? EM will be EK plus EP, and you will know, maybe sometimes they will give you the velocity of the bullet, or they will say it is stationary at the highest point, because you will see as the topics progresses, there will be the next topic that will be dealing with what will happen if the object moves and then it returns, what will happen before it returns. Those are the principles that we'll deal with. But now you need to know that there are such questions whereby we deal with what? With pendulum. So number one, if you are dealing with this pendulum, state the law of conservation of momentum in words, like in this activity. Use energy principle to show that the magnitude, you see, they say energy principle. Even though some of the questions we can use the equation of motions to calculate them, but when the examiner say use this specific principle, you are not allowed to deviate from what is being instructed to you. So they want you to use energy principle to show that the magnitude of the velocity of the bullet system, of the block bullet system, is 1,71 meters per second. So they want you to show that the velocity of this bullet block system is 1. So obviously what you are going to do, you are going to use that formula of the mechanical energy to solve that this bullet. Let me go back. Already we have the mass of the two, and then you want the velocity as it was moving at that system. So you will definitely use this formula of half mv squared and prove that this v squared with your calculator. You know that the mass is half, the mass is gonna be 20. This one, we need to change it. Remember, it's in grams also. So to change grams to kilograms, because you cannot deal with two different units together. Remember, if they say block bullet, already they are moving together as one system. So, or as one system. So we also need to make sure that, because we are going to add the two masses, the grams are changed to what? To kilograms. By doing what? By dividing by 1,000. So you'll say 15 grams divided by 1,000, and then you will add the bullet, which is going to be, I think, 0,015, and then this one is 5 kilograms. So you will add the two and find the mass of the bullet and block system, and then that will be the mass that will substitute here. We are looking for the velocity. Remember, the mechanical energy is at this point, so you are also having the height, so you can also find what? The gravitational potential energy. So it means it's going to be mgh is equals to half mv squared. The mass at this point is going to be 5 is 1. I think it's going to be 16,5 if I'm not mistaken. We know the value of this one is 9.8, and then we have our 0,015 meters, which is going to be equals to half. The mass is still the same, 16,5, and then we're going to find v squared. Don't forget that our v is squared. So as the v is squared, definitely after getting your v squared, you must use a square root to find v squared. So that is what the examiner said. But now remember, you must prove. If your answer is not 1,71, it means there's something wrong, because what you are doing here, you are proving that your answer is correct. And then calculate the magnitude of velocity of the bullet just before it strike the block. And then also the police officer is pushed. Okay, this one is another one, but you can find this one. This is one question, and is a pendulum type of a question. So that is why I was saying to you, you need to be able to find the relationship between the two. So this, remember, is what I was talking about. They've changed the mass. We are saying the mechanical energy at the bottom is equals to the mechanical energy at the top. So they just use one thing at the same time. So what is happening here? We are having half mv squared. Remember, we don't know what is our final velocity, but this one is our mgh. As I was saying, we can equate the two as I was doing here. Remember, mgh is equals to half mv squared. And then after that, we find we equate the two. This one is the bullet mass and bullet mass block, which is 0,015 plus 5 multiplied by 9.8. Remember, this is our g, our gravitational acceleration. Is not new. And then this one is our, or is 0,15. This one is our height, the one that was shown on our, this height, this one, the one that was shown here of 15 centimeter. And then after that, you are going to find the v squared, and then this is not the v squared, but it's v. After getting the answer here, we used a square root. You remember the square root of this f squared, and then we proved that the velocity was 1,71 meters per second. We can also, for that other one, we can also use remember the formula of the conservation of momentum. Normally, we will start by showing that sum of momentum before is equal to the sum of momentum after, and then we use our formula, we substitute and find our answer. I think this was the second question that was asked on our question. So these are typical exam questions. Know that also in momentum we have graphs. Graphs are not only limited in some of the topics. Like this is the momentum versus time graph, and you need to know how do we interpret graph. You can see here you are given momentum, and here you are given the mass or the time that the time taken by this object. So we need to know what does a straight line mean. We need to know what does this mean. You know, it's very important to know what does each line mean. Obviously, from time 0 to time 20,1, it means we have our momentum is constant. It doesn't change. It's uniform. It's the same. And then from time 2,1 to time 20,1 to time 20,2, we can see that our momentum is decreasing. And also, so it is decreasing from 80,000 to 14,000. So we can find the change in momentum here. We can know that if this is our initial momentum, this one is going to be our final momentum. So we can find the change in momentum between time 20,1 and 20,2. And then also here our momentum between 20,2 and 20,3, our momentum become constant, and it is 14, so the change in momentum here is 0. Also the change here is 0, but here we can be able to find the change. So the graphs are very important, and we need to know how do we interpret the graph. And we also need to know that the system that we are dealing with is an isolated system, and all the principles that they say, what do you understand by the term isolated system, which is one of the terms that you must understand as you are explaining those principles in physical science, because you cannot keep on saying the system is isolated. We know that if the system is isolated, it means there are no any other factors or external factors that are affecting the system, depending on the context that you will be referring the isolated system on. I know we are just about to end our session, but let me just if we look at, let me just go back a little. Okay, just we look at this one here. They said, what do you understand by the term isolated system, and use the information in the graph to answer the following question. Number 1, they say calculate the magnitude of the velocity of car A just before collision. And definitely you need to, because here everything was normal, it means there was nothing that was happening. But obviously here, because there was a decrease in momentum, it means there was a change in momentum. It means that's where collision occurred. So for you to calculate that, just to deal with a graph, one question of a graph, you know that system which is not acted upon by external forces, as I was saying, this is how you can deal with the definition of isolated system, or system where there is no net or a external force exerted or acting on that specific system. So here, remember, this was, they said we must calculate the velocity just after collision. This was the momentum of an object. This was the mass, it was provided to us. We want the velocity of an object before collision, and we could find the velocity of an object before collision because this was what was provided to us, as the question was showing us what is expected out of us. And then also we can, I'm not worried about the questions that you can find. What I'm worried about is how do you understand about the lines on the graph, whether there's a change, whether there's an increase, whether it's a decrease, because that will also assist you to say there's a decrease in terms of the momentum of an object, there's an increase in terms of the momentum. And what does the decrease mean? What does the increase mean? Because they will always be affected by the velocity. So these are some of the questions that you can look at and try to solve the questions under momentum. I just want to look at the last slide, which is, thank you so much. Thank you for watching this today's lesson. I hope after this lesson you will just go back to the activity that you have done with your teacher and see whether whatever that we have discussed can assist you in even understanding more of the things that you are doing with your teacher. From my side, thank you so much for watching. Until next time, goodbye from me.